Hey guys, and welcome to this video. So in this video, I'm going to be talking about OSI Model Layer 3, or the network layer. Now this is a very important layer to learn about because the network layer is really the foundation of what the internet is today. So let's get started. A quick recap of what we talked about in the last video. So in the last video, we talked about the OSI layer 2, which is the data link layer. And the data link layer handles the logical transmission between devices on the same network. And it contains two sublayers. One is called the logical link control, where it defines the protocol format and encapsulation and decapsulation of frames, and it performs error detection, correction, and flow control. On the other sublayer is called the media access control, or the MAC, and that defines physical addressing and method to access physical media, and that is used to avoid collisions. We also touched upon two devices that operate at layer 2. We have the bridge and a switch. A switch is a superset of a bridge, and it's an intelligent device that learns about the devices that are connected to that switch. Now, it also creates a network, but most importantly, it solves a huge issue with collisions. Now, you may remember collisions is when you have multiple devices trying to communicate over the shared medium that they all use. And a switch separates each port into its own collision domain, so you cannot have collisions on the network. So that solves a huge issue, and it makes the network more performant. So let's get into the network layer. The network layer handles logical transmission between devices on different networks, as opposed to in OSI Layer 2, where it handles logical transmission between the devices on the same network. It performs three functions. One is logical addressing, then routing, and encapsulation into and decapsulation from packets. We start with logical addressing. A logical address uniquely identifies a device across multiple networks. It is assigned to a device and it can change depending on the context. So if I'm at home or at a friend's house or outside on a cellular network, I can potentially get a different address in all of these cases. Now, different protocols use different logical addressing schemes. Now, in practice, we've had one dominant protocol for the past few decades. So we've been using one logical addressing scheme. Now there's been updates to that protocol, and it has provided new features and new logical addressing scheme. So we're going to explore those in a future video. Like in layer 2, once we have addressing scheme established, then we can start communicating. Now we have unicast, multicast, and broadcast, just like in layer 2, but we have a fourth one called anycast. And anycast is a communication where the destination is one receiver out of multiple potential receivers. Now, especially logical addresses may be reserved for multicast and broadcast, just like in layer 2. Now, it's great we can start communicating, but how do I get to my destination? Because remember, in layer 3, we're talking about communication across multiple networks. And we already know how to communicate within a single network, and that is using layer 2, but I still need a way to communicate across multiple networks, for example, around the world. So how do I do that? Now in layer 3, it provides a function called routing. And routing is the process of directing packets to their destinations. And we use a device called a router to route or direct packets to its destination. And we can connect multiple routers together to form large networks. Each router in the network is a hop to its destination. And all the hops and links that packets go through from a single source to a single destination is called a path. So here's a very simple routing example. So let's say we have a packet that's coming into router 1 and it needs to go to destination A. So there's some decisions that are made, whether it's by a human or by the router, but it's going to determine a path. And here's one path that can be taken to get from router 1 to router 11. So it can go through router 1, router 6, 7, 10, and then 11. Now this is great, but how does a router know where to send a packet given a single destination? Well, routers need to build something called a routing table. A routing table is basically a list that tells the router how to reach all the destinations. Now, route is an entry in the routing table that directs packets to a single destination, and it contains the destination network and the next hop. Routers make decisions by matching the destination address of a packet with one entry in the routing table. And the key here is the matching of the destination address, and it does not check the source address. So that has security implications, and we're going to explore that in a future video. Now, if there's no route that is found in the routing table, the packets are discarded. Now, we can use something called the default route that can be used when no other route matches. But how does a routing table get all of its entries? Well, there are three different sources. Number one is directly connected networks, and that's pretty self-explanatory. But there are two other route types. One is called static routes, and second is the dynamic route. For static routing, the route to a destination is fixed because you're telling the router exactly where to send the packet for a given destination. Now, it is simple and easy to configure and implement. And on most devices, it's just a matter of typing in one line of code. Now, static routing is not suitable for large complex networks. It is difficult to manage large number of routes, and it does not take into account changes in networks. And it also provides no optimization, so your network may not perform as well as it can be. Now, the path to a destination can change as a result of changes in the network, and that's why we use something called a dynamic routing protocol. A dynamic routing protocol is a protocol used to make routing decisions automatically. And there are three main functions performed by a dynamic routing protocol. First is collect routing information from other routers, and second is to calculate the best path to all destinations. And if there's any updates from the network, process those updates and recalculate the best path to all the destinations. And when all routers are at a stable state and it has consistent routing information, the network is said to have reached convergence. Here is the routing example that I provided earlier. If you recall, we have a packet going to destination A that comes into router 1, and it takes the path router 1, 6, 7, 10, and 11. Now let's say a router on the path goes down. Let's say router 6 goes down. In static routing, because the routes are all fixed, you can no longer route the packet to destination A. Now in dynamic routing, all the routers on the network, or the remaining routers on the network, will work together to create a new path, right? So now, once it converges, it'll take a new path, and that path could be router 1, 2, 3, 8, and 11. So that's a benefit of dynamic routing protocols, where it takes into account changes in the network. Due to the added intelligence, dynamic routing protocols are more complex to configure and implement, but it enables larger and more complex networks, and different optimizations are performed depending on the protocol, and those include the number of hops, bandwidth, delay, and more, and each of these optimizations have benefits and costs. A huge issue that needs to be solved in routing is called routing loops. And routing loops occur when packets are being forwarded back and forth among two or more routers in an infinite loop. Let's take a look at a routing loop example. So let's say we have a packet going to destination A, and it doesn't matter where destination A is. In router 1's routing table, it says, well, for destination A, go to router 2. So router 1 forwards the packet to router 2. In router 2's routing table, it says for destination A, go to router 3. So router 2 sends the packet to router 3. In router 3's routing table, it says for destination A, go to router 1. So it sends the packet to router 1. And at this point, you've gone from router 1, 2, 3, then back to 1. And that's a loop in the routing. There are two major causes of routing loops. The first is the network has not converged, and this tends to happen in large networks and in networks where the protocol used has slow convergence. Now, you might experience some temporary issues, but the issue will largely resolve itself once the network converges. But a misconfiguration is a bigger problem because it is permanent, and that can have great impact. The most obvious impact is not being able to reach the destination network with a routing loop, but it can have much worse impact than that. It can slow down the performance of your entire network, or in the worst case scenario, it may bring down a huge part of your network or even the entire network. And from personal experience, this tends to happen more often than not, because when you have a routing loop, a router needs to process the same packets over and over again, and it overloads the router's resources, causing it not able to process packets from other traffic or even causing it to crash. So when you are designing a network, make sure your network is free of routing loops. There are different ways of classifying routing protocols, and we're going to look at two: purpose and operation. To talk about the purpose classification, we need to learn about autonomous systems. An autonomous system is basically a network under the management of a single entity. Now, there are two types of routing protocols under the purpose classification. The first is called the Interior Gateway Protocol, or IGP, and that is a protocol designed to make routing decisions for networks within an autonomous system. And the second is the Exterior Gateway Protocol, or EGP, and that is a protocol designed to make routing decisions among networks from different autonomous systems. Next is the classification based on operation, and there are three types. The first is called the distance vector, second is the link state, and third is the path vector. For distance vector protocols, the network information is exchanged between directly connected neighbor routers, and each router advertises the known distance, which is the cost, and the vector, or the direction or next hop to each destination. Now, route calculations are performed based on neighbors' reachability to destinations, which means no router has the details on the full network topology. Routing updates include the entire routing table and sent periodically, and that is not very efficient. Now, it is simple and easy to configure. It has low resource usage, but the routes may not be loop-free, and it is mainly used by IGP protocols. In link state protocols, network information is sent to all routers on the network. Each router advertises details on its own connected networks. And route calculations are done on the entire network topology, which means each router has the details of the full network topology. Now, routing updates are sent only upon topology change, and it includes only the networks that have changed, which is much more efficient than distance vector. However, due to the added complexity and intelligence, it requires more expertise to design, configure, and implement link state protocols. It also has higher resource usage because it needs to carry the full network topology information and also carry out the calculations on the full network topology. However, the resulting routes are loop-free, and link state protocols are used by IGP protocols. Lastly, we have the path vector protocol, which is a modification of the distance vector protocol. In path vector protocols, network information is exchanged between directly connected autonomous systems rather than directly connected routers. Each router advertises the known distance and the path to each destination. Route calculations are performed based on neighbors' reachability to destinations, which means path vector protocols do not have the details on the full network topology because it is more concerned about paths through autonomous systems rather than the routing inside any autonomous system. Now, routing updates are sent only upon topology change and include only the networks that changed. But due to the added complexity and intelligence, it requires more expertise to design, configure, and implement. It also has high resource usage because it carries a lot of route information, but it ensures that the resulting routes are loop-free, and it is used in EGP protocols. These are some of the references that I used to make this video, and that's it. So I know it's a lot of information, so feel free to go back and rewatch this video, but it is crucial to learn and understand all the concepts in network layer. So please like and subscribe and comment down below. Let me know what kind of security issues that you can think of that may happen at the network layer. Thank you, and I'll see you in the next video where I will talk about OSI Layer 4, the transport layer.